All right, for this problem, we're asked to find the largest possible volume of a box that can be inscribed inside this ellipsoid. 2x squared plus y squared plus 4z squared equals 12. So first, let's think about what this ellipsoid is going to look like. If we put this into a form that we recognize for an ellipsoid, if we divide both sides by 12, we're going to get x squared over 6 plus y squared over 12 plus z squared over 3 is equal to 1. So if we graph our ellipsoid here, we're going to, on the x-axis, we're going to go out square root of 6 on both sides of the origin. On the y-axis, we're going to go out square root of 12. On the z-axis, square root of 3. So we're going to get this kind of potato-shaped ellipsoid here. And I'm not good at drawing this in terms of, let's just kind of make some sort of effort to make this look three-dimensional. But anyway, we've got this potato shape here. And we want to know what rectangular box, what's the maximum volume of a rectangular box that we can inscribe inside this ellipsoid. So we've got this little rectangular box in there, and we want to figure out what's the maximum volume of that box. Okay, so what we need to do, this ellipsoid is our constraint. We need to come up with a function for the volume of that box. Well, volume is equal to length times width times height. Our length here is going to be, we're going to go out x units on either side of the x-axis. So we've got x and minus x going out on either side here. So that's going to be 2x. The length will be 2x. The width, since again this is centered on the origin, so the width is going to be 2y, and the height is going to be 2z. So our function f of x, y, z is going to be equal to 2x times 2y times 2z, so 8x, y, z. That's our function for the volume of this box. And this 8 is there because of the fact that we're centered on the origin. So however far out we go on the x-axis, we got to go, the length is going to be twice that distance. All right, so now let's take that function, let's put that up here. That's our f of x, y, z is equal to 8x, y, z. And now we can use our method of Lagrange multipliers to figure out the maximum for this function subject to that constraint. So we know that the gradient of f has got to equal the gradient of g, which is this function set equal to 0, times some multiplier, some constant lambda. So the gradient of f is going to be the partial derivative with respect to x, which would be 8yz times our unit vector I, plus the partial derivative with respect to y would be 8xz times j, plus partial derivative with respect to z would be 8xy, and that's times the unit vector k. There's our gradient for f. Our gradient for g is going to be 4x plus 2y times j plus 8z times k. All right, and so now we know that gradient of f is equal to the gradient of y times some lambda. So this 8yz has got to be equal to 4x times some lambda, and 8xz is equal to 2y times some lambda, And 8xy is equal to 8z times lambda. That's an ugly lambda. All right, it's off the screen anyway. Okay, so let's figure out what lambda is from this equation. So if we divide both sides by 4x, we get that lambda is going to be equal to 8yz divided by 4x, which is going to be 2yz over x. Now let's use that lambda and plug that in over here. So we get 8xz is equal to 2y times all of this. So let's see, that's going to be 4y squared z over x. Then if we multiply both sides by x, we're going to get that 8x squared z is equal to 4y squared z. If we divide both sides by 4z, we're going to get that y squared is equal to 2x squared. All right. And then if we use our lambda again over here, we're going to get that 8xy is equal to 8z times our lambda. So this is going to be 16yz squared over x. Multiply by x, we get 8x squared y is equal to 16yz squared. And if we divide both sides by 8y, we're going to get that x squared is equal to 2z squared. All right. So now we can use these values here. I'm going to erase everything up to here. Now we've found these relationships between x and y and x and z, and we're going to use that and plug that into our constraint up here. So 2x squared, we get 2x squared plus y squared is 2x squared, and 2z squared is equal to x squared, so 4z squared is equal to 2x squared. So we have 2x squared plus 2x squared plus 2x squared equals 12, so 6x squared equals 12. Divide by 2, we get x is equal to plus or minus the square root of 2. All right, and then let's go ahead and use this value. So if we plug that in here, we get 4. And y squared is equal to 2x squared, which is equal to 4z squared. So y squared is 4z squared plus 4z squared is equal to 12. So we get 8z squared is equal to 8. So z is equal to plus or minus 1. And then let's plug in both our x and our z. So we get 4 plus y squared plus 4 times z squared, which is this 1, is equal to 12. So y squared equals 4, so y is plus or minus 2. All right, now we can get rid of this, because now we know that x is plus or minus square root of 2, y is plus or minus 1, plus or minus 2, and z is plus or minus 1. Obviously, we're going to go with the positive because we're trying to maximize our volume here. And so our volume, our max volume is going to be 8 times x, which is the square root of 2, times our y, which is 2, times our z, which is 1. And so our maximum volume is going to be 16 square root of 2.